So our first detour, reductions. Now we've actually seen reductions now, but I'm going to introduce a new term called cracking that I think will make this whole line of reasoning easier to understand. So reductions we saw during our discussion of puppy, cat, dog, and what we can do is, just as a reminder, we informally say that a problem x reduces to problem y if an instance of x can be transformed into a useful instance of problem y that solves x. Okay? Well, I didn't use that definition before, so that probably seems like gobbledygook. Okay? So let me give you an example. I think it'll make it much more concrete. Let's suppose x is median finding ignoring all zeros. That's the problem I'd like to solve. Okay? And let's say that sorting is some other problem that we want to maybe use. Okay? So for an example, suppose we want to find the median ignoring zeros of 99.5, 87.3, 92.5, 62.5, and 89.2. So what we can do is create a new array which has none of the zeros, okay? Sort it, and then return the middle item. So in that sense, we've taken an instance of problem x, here it is, it's this array, and we're turning it into an instance of problem y that can be used to solve x. In this case, we threw away the zeros. Okay? So in that case, we could say that the problem of median finding ignoring all zeros reduces to sorting. That is, well, you could just use sorting. That's why you can think of it as the word reduces to. Now there's some passive voice issues that I found that in an introductory course where we don't have a lot of time to build intuition about the term reduce, I think the word's almost the wrong direction. So I'm going to introduce a new phrase, cracks, or a new word, cracks. Okay, so in this lecture, I'm defining my own thing. No one else in the whole world uses this, but I find it useful just for this course, for this specific lecture, which is to say that a problem y cracks problem x if x reduces to y. So as an example, sorting cracks median finding ignoring all zeros. It's like a key, you know, it's like, imagine safe cracking. It's a way to access the solution to the problem. Sorting cracks the case, right? You've solved it. And you'll find that this whole discussion makes much more sense when we're using the active voice as opposed to the passive voice, wimpy reduction. Okay? Another example we had from before, we've seen this already in our earlier lecture, the problem of sorting also, by the way, cracks the problem of puppy, cat, dog. And that was an insight we used to place a fundamental limit on the sorting problem. Okay? So what we're going to do here is introduce out of nowhere another problem called 3-set. And the reason we're going to do that will become clear soon. Okay. So hopefully the notion of cracking makes sense. Now we're just taking another like sub-detour. So given a Boolean formula, the 3-set problem asks, does there exist a truth value for the Boolean variables given in that formula that obeys a set of 3 variable disjunctive constraints? Okay, what does that mean? Well, here's a 3 variable disjunctive constraint. Disjunction is like or. So there are 3 variables here. Each one can either be a particular variable or the negation of a variable, and together they form a constraint. That is, either x1 must be true, or x2 must be true, or not x3 must be true. And then in 3-set, there's a set of these constraints. They're constraints because they must all be true. So one constraint is that either x1 or x2 or not x3. Another constraint is either x1 or not x1 or x1. And I will note that this one's trivial, because no matter what, this one's always satisfied. It doesn't matter what x1 is. And then we have x2 or x3 or x4. So one particular solution for this set of three variable disjunctive constraints is x1 is true, x2 is true, x3 is true, and x4 is false. That is, plug it in, right? x1 is true, okay, that one's covered. x1 is true, well, that one's trivially covered. And then because x2 is true, that's all we need, really. If x1 is true and x2 is true, then this whole expression is true. Right? It doesn't much matter what goes on here. Okay? So, here's the thing I'm going to note. The problem independent set cracks 3-set. Okay, so now that we understand what 3-set is, hopefully, what I'm going to note is that the independent set problem cracks 3-set. Okay, how does that work? Well, just like we did earlier, where we took an array that had some number of items, took out the zeros, passed it to sorting, and solved the problem. Here, we're going to take our independent set, we're going to take an instance of 3-set and create a version of independent set that cracks our problem, that solves it. Okay? So in other words, let's suppose we have an instance of 3-set. I'll call it phi. I'm going to create an instance G of independent set that has the following properties. For each clause in phi, I'm going to create 3 vertices in a triangle. And this is actually a pretty challenging thing to come up with. A lot of times reductions are tricky. You know, they're not as easy as this one. So this one I'm just spoiling. I didn't even give you a chance to think about it. And then what I'm going to do is, after I've added those 3 vertices in a triangle, I'm going to add an edge between each literal and its negation. The intuition being they can't both be true in 3-sat, which means they can't be in the same set in independent set. Okay? So in other words, imagine here that we have the 3-sat expression, x1 or x2 or x3, and not x1 or not x2 or x4, and not x1 or x3 or not x4, and x1 or x3 or x4. Okay? How do we find a set of variables x1, x2, x3, x4 that satisfy this? Well, what it can do is I can create an independent set instance following those rules. So let's look at each of them. Here's a 3-variable disjunctive constraint. Okay, here's x1, x2, x3, added lines between them. Same deal here, and same deal here. So this one is not x1, x3, and not x4. And then we add a line between each variable and any place that you see its negation, x1, not x1. We're going to add lines between those. Okay, and it turns out that if you make this construction, and we'll see why in a moment, this constructed graph, if you already had a magical independent set solver, they would also solve this original problem we had in 3-sat. So what I'd like you to do is understand what we've been talking about, because this has been quite an earful. It's a lot to process. So your first goal is, given this expression in 3-sat, understand how I use these steps to get this graph. You don't understand why, just how. How did I get from this to this? And then the more interesting thing will be to say, okay, once you find an independent set in this graph here, how does that help you figure out a solution to this 3-sat problem? So in other words, for k equals 4, find an independent set, and then think about how that solves this original 3-sat problem down here. Okay, so give those 3 tasks a shot. First, understand how I got from this expression to this graph. Second, find an independent set in this graph. And then third, figure out how the independent set you found solves this 3-sat problem. And I really want you guys to sit down with this one and think about it carefully, because this is, obviously a tricky topic to digest. Okay, so there's many possible solutions to this independent set problem. So I'll give you one. This one, for example, we could say x3 is true, x4 is true, or sorry. So there are many possible solutions to this independent set problem, right? One of them is color this vertex red, this one red, this one red, this one red. And if I do that, you'll notice there's 4 red vertices and no 2 red vertices touch. Okay, so that is a solution. Now the second part was, how does that solution to the independent set problem help me? Well, I can actually just say that any vertex I colored in red is true, and anything white is, well, or sorry, anything that's red is, that statement there is true. Anything white is, we don't really care. So in this case, we're saying x3 is true, x4 is true, x3 is true, x4 is true. So one possible solution to this 3-sat problem is that x3 is true, x4 is true, and we don't even care what x1 and x2 are, and that will satisfy the constraints. Let's see another one. I could have also done x1, not x2, x3, and x4. So I'm saying all 4 of these things are true, and that will actually also satisfy my expression. So x1 true, x2 false, x3 true, x4 true. So that's another solution. I mean, it's no better or worse than this one, and both of them are fine. So I hope it's now clear how it is that if I take a 3-sat instance and I turn it into a graph with that certain structure following the rules that added these edges, it gives me a solution to 3-sat. So in other words, what we now have is an n squared times 2 to the n solution to 3-sat. First, construct a graph. Second, use our independent set problem. Independent set cracks 3-sat. Okay, so what? Independent set cracks 3-sat. Who cares? Well, recall that our goal was to understand, can we place some more fundamental limit on the ultimate independent set algorithm? So what can we say about the worst case runtime of Twisa? Well, before we were able to say it's at least n, and no worse than n squared times 2 to the n. And so the question is, now that we've done this work, can we say more? Sort of. Well, we know that Twisa can crack 3-sat, or that independent set cracks 3-sat. So if somehow we had a lower bound on 3-sat, we could apply it to Twisa, right? We could say there's no way to do independent set any faster, because that's just the rules. Like, if 3-sat is fundamentally takes bleep blorp work, well then Twisa needs to take at least bleep blorp work if it can solve 3-sat. And so it's basically the same thing we did with comparison sorting and puppy cat dog. Now, unfortunately, there's no known useful lower bound on 3SAT. But this is actually useful, this whole set of frameworks, because it allows us to be an educated citizen. So there's a lot that we're ignorant about in computer science. And to understand the taxonomy of our ignorance, we're going to take a detour into what's known as complexity classes.